Hi everyone. Today we are going to talk about optimizing AI machine learning workloads in Kubernetes. We are going to specifically talk about machine learning pruning as a use case for efficiency and scale. So my name is Achyut Boggaram and my co-speaker is Shashidhar Shenoy. So let's get started. So as you can see, the recent trends since 2022 in the major large language models landscape, if you look at that graph here, you can see we are going like bigger, bigger, bigger. We reached almost a trillion parameter models. And slowly we can see that now we're going a little smaller in terms of model size while maintaining the same level of performance in terms of accuracy. And also, we are gaining more abilities for these models like reasoning, and these models are becoming more specialized for math, coding, and things like that. So there has been a ton of innovation in training these models, fine-tuning these models, extending the context window like RAG and things like that. But no one is talking about how to efficiently deploy these models to get the best performance per watt on your GPUs and best performance per dollar. So some of those techniques to efficiently deploy these are like model compression techniques to make the model smaller after they're trained or during training. And we'll talk about machine learning model pruning specifically today. But I want to pose some questions about like, okay, this is a great concept, but how should we actually like deploy a sparse model that you would generally schedule a dense model to in terms of the node capacities? Can memory aware scheduling improve your bin packing algorithms for your enterprise resource pools? What if we expose some of these model pruning metadata for the scaling infrastructure so that we can make intelligent scaling decisions and the infrastructure can actually make intelligent choices? Think about that. Now, I talked about model compression techniques, and there are like broadly three categories: machine learning model pruning, quantization, and knowledge distillation. Knowledge distillation, as you might have all heard about, is really like transferring the knowledge of a bigger model to a smaller model and deploying the smaller model to the final production. But you don't deploy the teacher model, and you generally jointly train these models. Quantization, you reduce the numerical precision to like 16 bits, floating points, or like int 8 or even int 4. And you can achieve very good throughput gains. You can get very good model compression. Um, but these two techniques, knowledge distillation and quantization, can be applied relatively after like training, and they're not really heavy in terms of the infrastructure complexity in terms of applying these workflows or orchestrating compute for these workflows. However, machine learning model pruning is a very surgical and scientific approach, and it requires a little bit more complex infrastructure algorithms because the model structure itself changes, as we'll see in the upcoming slide. But the throughput gains are max very good, and the compression ratio is like very very high. And this is like generally applied either during training, before training, or post training. And there's a lot of very interesting theory that has come out in the recent years. So let's check that out. So, what is machine learning model pruning? It's literally the idea of removing redundant weights or weights that don't generally contribute to the final inference outputs. So think of these like for example, have a machine learning model weight that is below a certain threshold, you simply zero it out, and that is an example of unstructured pruning. There's also structured pruning approaches where you simply remove the entire subgraphs, and you can do this either randomly and see if you can like literally fine tune it a little bit and achieve the same level of performance. And this is a seminal work that's called lottery ticket hypothesis that's recently coined. And this is fascinating, right? Why do some of the subgraphs that are literally replacing the entire like layers and neurons don't contribute to the output? But it's a fact. And how is it different from maybe training a smaller model from scratch? It's significantly better in terms of training a bigger model and then removing subgraphs or removing like some of these weights than training a smaller model from scratch. And on average, it's 15% better in terms of performance. And We only like prune the machine learning model weights and not the biases, because if you prune the biases, your performance degrades quite heavily. And there is a good primer I wrote about machine learning model pruning. It's a more comprehensive guide. Please check it out. Now I want to talk about the real world case study with some real numbers on real model, right? So NVIDIA released this Minitron family of models. They took Llama family of models and they reduced the size by like 4 times. They also gained 3 times throughput gains. They literally did pruning iteratively and fine tuning, along with knowledge distillation, of course, but they also like talk about some of the best practices for Llama family of models. They prune like depth wise, breadth wise, and things like that. There are a lot of best practices that they talk about in their blog post, but they don't really talk about how to deploy these models in the infrastructure. Even for their specific hardware, they have a white paper, but they don't really talk about the infrastructure challenges or orchestrating compute for such workloads, deploying these at scale, like multiple hundreds of models. There are many, many challenges associated with these very surgical, very scientific approaches, and they're not often discussed in today's world. And that's what our talk will focus on in the upcoming slides. With that, I'll hand off the mic to Shashi to talk about some of the real world challenges in deploying machine learning model pruning workflows in Kubernetes.
Achyut, for introducing us to pruning and kind of walking us through the benefits. Now let's look at how to productionize these systems um, in the real world. So one of the things as infrastructure engineers is how do we kind of enable our systems to be pruning aware, and for that we'll require some kind of metadata. One of the metadata that we could use is the model sparsity. And the objective of this is to make sure that we plumb it into the system with minimal rewrites while keeping maintainability and fault tolerance in mind, and also making sure that this brings in the maximum gains in terms of efficiencies for our infrastructure. In this slide, we will look at a canonical example model pipeline. The important aspect of this pipeline essentially is everything here is kind of open source Kubernetes ecosystem. The reason why we want to choose something like this is to take the maximum benefits of the evolution that and improvements that keep happening in open source systems and the guidance that you can get from community while contributing back to the general ecosystem. Okay, so in this slide, what we'll look at is we will use the previous slide as an example, and then kind of see what are the different changes that we need to make. And the key guiding principle would be we want to keep the changes minimal, but at the same time see how we can pass different signals. In this case, for example, sparsity ratio through different aspects like orchestration layer, the scaling layer, and so on and so forth. And so that we make our existing systems pruning aware. Okay, in this, what we'll do is we'll zoom into like the orchestration part of it. And if you notice, this will be like your typical YAML. We have hidden the different things that are in YAML and only focusing on the things that are of interest here. So if you notice, we are passing the model sparsity, which is like 0.65, the random value we have chosen. And what we are saying here is that we could kind of map it to like a DRA claim. Now, people that are not familiar with DRA is something that will help guide the pods into a specific type of node at the orchestration time. For more information, please feel free to kind of look at the documentation related to the DRA. And the other aspect is that we'll also use sparsity levels and inject this into our pods for for changes during the runtime for these pruned models. One thing that I want to kind of mention here without being too prescriptive is that we can think of this model sparsity as a spectrum. Like you can have like a range of values mapped to single DRA. The benefits of this would be something that we will discuss in subsequent slide. Okay, so we're going to build on our previous discussion, which was related to the orchestration. And in this case, we're kind of focusing on the scaling aspect of things. Now, if you think of web scaling, or rather like scaling for web loads, we will think of like scaling using like low-level metrics like CPU usage, memory usage. Whereas here we are kind of focusing on macro signals like what is the back pressure on our inference job, how much jobs are pending to kind of guide our scaling decisions. And this is where KEDA fits into the whole system. And this is something also which is part of the Kubernetes ecosystem that we could leverage. And in this case, for example, you could use the queue depth as a guiding parameter, and just tied to our previous conversation, you could have like a range of sparsity values mapped to a specific queue, and then that will be mapped to specific DRA claim. This way, you have like your entire orchestration and scaling layer all nicely tied up and leverage different Kubernetes constructs. Okay, like any other system, the discussion is not completed without kind of acknowledging and discussing about the trade-offs and challenges, right? So we have kind of discussed how we can leverage the existing Kubernetes construct. But one thing that we want to point out here is that there is no canonical or standard way of doing things. This means that the engineers have to get creative. For example, in our case, we are kind of using model sparsity as a guide for basically making the infrastructure pruning aware. One of the reasons for doing that was to identify what is that 20% or like smallest parameters that we could choose that will give us the like the 80% of the benefits, right? Something like an 80-20 rule. But different engineers could do it in different ways, and there is some fine tuning that would be required here. That way, you will not end up in either like a situation where overscaling or underscaling. Overscaling might lead to like underutilization of resources, and underscaling would lead to dense models and the pruned models being on the same node. Having said all these things, we still feel that there is a lot of value that the infrastructure would unlock by making it pruning aware. So this is something that we definitely encourage users to adapt to. Okay, so now that we are at the end of our discussion, I want to kind of highlight two things. One thing is that the infrastructure engineer should focus on identifying the smallest changes that could make their systems, in this case, like pruning aware. Like for example, choose one parameter with like the model sparsity and see what are the minimum things that you need to do to make and pass it through the system to make your pruning aware. And we kind of walk through the example. And the second part is the how you can unlock the benefits of like leveraging like Kubernetes ecosystem by adopting a lot of open source tooling. That way, you're growing with the community as the paradigm and the model evolves. Once again, we thank you for joining us for this talk.